Hello friends, today we shall talk about linear programming. This is also called LPP, that is linear programming problem. The purpose of linear programming problem is to find best solution keeping constraints in mind. There are some terms associated with linear programming, that is objective function. This is written as z equal to ax plus by, where a and b are constants, xy are decision variables. This is a linear function which needs to be optimized. Constraints or restrictions or limitations. Now we have to understand what is a feasible region. If I have one line like this and another line like this, then this point, corner point, is called feasible solution or feasible point. This is called feasible area. This is called optimal point. The solution will lie within this area or on this region. We will understand the concepts with an example. Find maximum value for z equal to 5x plus 2y from graph. This is the objective function. The graph looks like this. This is the origin, this is the x-axis, this is the y-axis. I have some values here: 0, 40, 0, 50. This point of intersection is 20, 30. This point on x-axis is 30, 0. And this point is 50, 0. This is the feasible region. This is the region that is common to both the lines. These lines are drawn using constraints. So now we have corner points, that is this and this. We have to consider those corner points within which the feasible region is enclosed. Now we have the objective function written here. The corner points are 0, 0. Substituting for x and y, I get 0. Another corner point is 0, 40. Here I get 80. 2 into 40 is 80. Another point is 20, 30. I get 100 plus 60, that is 160. This is 30, 0. Here I get 150. Of all the values, this is the maximum value. So this function 5x plus 2y has maximum value when x is 20 and y is 30. This is the inference we get. Finding the best solution is also called optimization. When we optimize, we either look for maximizing or minimizing. Now we'll do another sum for minimizing. Find the minimum value for z equal to 2x plus 7y from graph. The graph looks like this. So we have 4 corner points. We have actually 5. 1, 2, 3, 4, 5. And this is the feasible region indicated. These are the corner points. Here we have to find corner points and substitute in the objective function. Here objective function is 2x plus 7y. X and y are constraints. Upon substitution we get 140 here. Next corner point is 1, 15. Here I get 2 plus 105, which is 107. Then I have 15, 10. This yields 30 plus 70, that is 100. Next it is 20, 0, that is 40. So the minimum value here is 40. The minimum value lies at 20, 0. Now we'll do another type of problem. Solve graphically and maximize the objective function z equal to 5x plus 3y. The constraints are x plus y should be less than or equal to 6 and x should be greater or equal to 0. Y should be greater or equal to 0. Now the graph given looks like this. Zero, 10, and this is the feasible region. Here we have only 3 corner points. Now I write down the corner points and substitute in objective function. At origin objective function is 0. At 0, 10 this yields 30. At 8, 0 this objective function yields 40. So the maximum value is 40 when x is 8 and y is 0. Now I have a practical problem to solve. A manufacturing company manufactures pressure cookers and pans. The company can manufacture 300 pieces at most a week. So this is one of the constraints. The cost of manufacturing pans is rupees 1800 and cookers is rupees 2700. The company can spend not more than 6,48,000 rupees per week. The profit gained for pans is rupees 510 per piece and rupees 675 per piece for pressure cooker. How many pans and pressure cookers should be manufactured to get maximum profit? As we already discussed, the main aim of LLP is to maximize or minimize. So here we have to identify the objective function and the constraints associated with it. Here we know that 300 pieces can be manufactured. So I write let X be the number of pans, Y be the number of cookers. We know X and Y, that is number of pans and number of cookers, should be less than or equal to 300. This is the first constraint. The second constraint is 1800 plus 2700 Y should be less than or equal to 6,48,000. That is, the cost spent for manufacturing cannot exceed 6,48,000. So this is the second constraint. This can be written as 2x plus 3y less than or equal to 720. The object function is 510x plus 675y should be maximized. This is the objective function or the linear function. Now consider x plus y equal to 300. We'll substitute for x and y. When x is 0, y becomes 300. When y is 0, x becomes 300. So we have got the end points of this line. Now consider another equation. 2x plus 3y equal to 720. For this we will find out different values. When x is 0, y becomes 720 by 3, that is 240. When y becomes 0, x becomes 360. We got the contours. Now we have to solve these simultaneous equations. We will get the values for x and y which intersect. The point of intersection of these two lines we will get if we solve these simultaneous equations. X plus y equal to 300. This can be written as 2x plus 2y equal to 600. Another equation is 2x plus 3y equal to 720. I am using elimination method. I am eliminating one of the variables. So we got y is equal to 120. I substitute in this equation and get x to be 180. Now I plot the graph. I have got corner points and the function. One is 0, 0. It is 510x plus 675y. Here I get 0. We have got one value to be 0, 300 and another value was 300, 0. This is one line. Another line was 0, 240 and another point was 360, 0. So this is the point of intersection. This is 180, 120. The region that is common to both the constraints is the feasible region. That is this region, feasible region. Now we will substitute and find out. The corner points are 0, 0, 0, 240, 180 comma 120 and 300 comma 0. So now we calculate. When you calculate, you get 1,62,000, another value 1,72,800, 1,53,000. Of all the values, this is the maximum value. So the profit is maximum when x is equal to 180 and y is equal to 120. We have already defined x to be number of pans and y to be number of cookers. This is the practical application of linear programming. Thank you.